Okay, thank you. Sorry for that delay. Darren, can you hear me?
Yep, we can hear you.
Okay, great. Had a few last minute issues. So thanks everyone for joining this webinar. This is a subject that's has been near and dear to my heart, and it's been fascinating watching stove technology progress. And I want to thank our speakers for joining and telling us about their experience. Okay, next slide. A few housekeeping. For one, today, just use the Q&A function for any message you have, including, you can ask questions to the speakers at any time, and they will remain in the Q&A. So just ignore the chat. Everyone will be sending out a link to the recording and the slides afterwards, in case you miss any of it. Next slide. Okay, a little bit about us. We are a very small independent nonprofit. We have 4 employees, which is at the top row of those photos. And then some of our board and advisory board is below. We're based in Maryland, and we've been going since 2009. And the organization has been, funded in various ways over the years, and mostly it's from the U.S. Forest Service right now. Next slide. Okay, so today what we're talking about is really how to minimize smoke in the real world. And the problem, as I see it, is really with manually operated stoves. Because the goal you see in the test lab, you can see the Eco Design Ready stove, it's the European name, can produce a small amount of smoke compared to older stoves or open fires. But the problem is that same stove can produce the same amount as a 10-year stove or the open fire if it's poorly operated. So the goal here is to keep that eco-ready stove with that small green plume. And that has vexed stove manufacturers, not for decades, but for centuries. Our last webinar was on Ben Franklin, and he was working on these issues. And some of maybe the beginnings of automation were occurring during his time, where they were trying to figure out how to keep a stove in a more steady state. So solutions, restrictions or bans on where stoves are installed, stricter emission limits, improved test methods, or ensure sufficient airflow through sensors and automation. So I believe the last one has not been given enough attention. The first 3 have been actively debated and are being worked on by hundreds of people, spending millions or tens of millions of dollars. But I don't think stricter emission limits or improved test methods is going to get us that far compared to the variability that you get with manual operated stoves in the hands of consumers. So if we really want to clear up our air sheds, we need to see technology change. Next slide. Okay, so a little bit of background in some of our efforts. So we launched the Wood Stove Design Challenge in 2013, and Brookhaven Lab has been a consistent partner with it. The first 3 of them had NYSERDA backing, then DOE backing. And the goals have always been to spur innovation through competition and to engage government agencies to support modern wood heat. And DOE, thankfully, is still engaged in this as a result of this competition. It's also really to engage industry, universities, nonprofits, and others to reimagine what wood heat can be. Next slide. Oh, and sorry, go back for just 1 sec. I just want to show you all the entities who've been partners in this effort, other than those who have funded it. CSIA, HBBA, Lignetics, BTEC, Testo. Okay, next slide. So the basic task here is to do what's regularly done in boilers in a stove. So pretty much every single wood boiler or pellet boiler has a kind of automation that we would like to see in more stoves. And this has been going on since the 1990s. And in Europe, the I think it's standardized more quickly, and there's broad adoption of both thermocouples for temperature sensing and lambda controls for oxygen sensing in Europe and now here as well. So, question is, why has this not been able to translate to the stove? It's the same technology in a smaller box, and that's I think we'll be hearing that from our speakers shortly. Next slide. I wanted to show, there's currently actually in America, we don't have any manufacturer in North America of smart stoves. The Catalyst is off the market. Napoleon, I'm not sure if Napoleon's ever came to market. I know SBI is working on one that will be on the market soon. But right now, there are at least 6 automated smart stoves in Europe, 3 in Germany, 1 in Austria, Denmark, and UK. I think the Charnwood, and we'll be hearing from its manufacturer, Hugh Wells. Charnwood may be the only one that's on the market in the States right now. And the others, I think they found that the US market is a little too small for the cost of certification. But hopefully that too will change. Okay, next slide. The 3 panelists are Ken Davis, Paul Laporte, and Hugh Wells, and we are going to start with Ken. So Ken, if you want to pull up your
And I'll go ahead and
slides.
launch our first poll as well while Ken gets his slides up.
And I'd like to, as a little intro, Ken is a product designer at Sherwood Industries. They manufacture Enviro pellet stoves. But he's been involved in developing advanced wood stove technologies for nearly 20 years, including integration of electronics to enhance combustion efficiency and user experience. Let's just give another minute for this first poll. What brings you to the webinar? So it looks like most of us are stove industry professionals. Darian, you want to announce the results when you're ready?
Sure. Yeah, most of us, like John said, are stove industry professionals, but we also have plenty of policymakers, researchers, educators, and then some people who are just curious, or at least one person who's just curious. So we're happy to have you.
Okay. Take that down, and Ken, I'll turn it over to you.
Oh, great. Thanks, John. Can everyone see my slide, the presentation?
Go ahead and put that in slideshow mode if you can, Ken. We see your.
Oh,
if you go over to that slideshow
yeah,
tab.
right there. There we go. And you guys see it there, or?
Perfect.
Oh, it's all good? Okay, excellent. Thank you all for being here. I want to begin by stating clearly that everything I'll be discussing today comes from my own perspective, based on over 15 years of product development and independent research in combustion systems and systems control theory. I want to thank John Akerley and the Alliance for Green Heat for creating this space for technical exchange. And I appreciate my current employer in supporting me to participate and contribute today. So, welcome everyone. I'm Ken Davis, and I spent over 15 years in the hearth industry. I was primarily focused on product development, designing, testing, and ensuring compliance of more than 25 certified combustion systems. I've also brought 3 certified combustion systems with electronics to market, each built on a patent-pending control algorithm I developed. Excuse me. These combustion systems are the engine in over 200 stove models, certified, compliant, and commercialized throughout the world. But along that, I've also had a deep personal interest in system dynamics and control theory. That started with my academic training and continued through my own research and experimentation. While my professional work focused on meeting compliance and production targets, I've always looked at combustion from another angle, as a system that could benefit from real-time feedback and adaptation. Electronics to me are tools that help execute that vision. So what you hear today is a combination of 2 perspectives: the day-to-day product designer who understands manufacturing realities, and from a system level approach asking, how do we manage instability? These are the questions I want to explore with you today. This isn't just about adding components to a stove. It's about understanding what we're really trying to solve and whether electronics offer a practical path forward. We'll look at what the actual problem is, not just on paper, but in the field. I'll share one example that shows how electronics can be applied to a wood stove, and I'll explain how I've come to view this challenge from both a product and systems perspective. These questions are meant to reframe how we think about both the challenge and the opportunity. This is not about gadgets, it's about performance and stability. Many wood heaters pass compliance tests, but struggle in real-world conditions. These tests are controlled, but the field isn't. Fuel quality changes, draft conditions changes, users burn differently. And even small deviations can make a clean burning product behave very differently. This is where electronics become valuable. They're not just for data. They enable a system to adapt in real time, stabilizing operation instead of assuming everything's perfect. That's why I believe electronics are not just useful, they're essential. This is a key point. We've already built good products. I've designed over 25 certified combustion systems. We know how to meet the standards. But when you take those same systems into the field, performance is often variable. It's not always because the design is flawed. It's because the environment, fuel, and operation are unpredictable. Users burn different fuels, draft changes, ignition conditions vary. These factors introduce instability that even the best designed stoves can't control on their own. So the real problem isn't the stove, it's the unpredictable system it's operating in. Once we understand that variability, not necessarily design, is a problem, the next question is, how do we manage the variability? Oh, I might have missed a slide here, did I? Oh, I think I missed a slide. Sorry, this is for this slide. Once we understand that variability, not necessarily design, is a problem, the next question is, how do we manage that variability? Electronics give us the ability to sense, interpret, and respond in real time. Whether it's changing fuel conditions or draft fluctuations, we now have tools that can track those changes. But components alone aren't enough. The key is the logic, the theory behind what to do with the information, and that creates true adaptability. With that logic, electronics don't just measure, they help stabilize. This example represents one perspective of my own, shaped by a background in system control, a passion for electronics, and years working in product development. The theory behind this approach began during my academic training and personal research. It centered on how to stabilize systems experiencing unpredictable inputs, something that's very relevant to wood combustion. When I had the opportunity, I tested that theory using standard components like thermocouples, microcontrollers, and airflow devices, just tools we all know. The result was a working model and a physical prototype that aimed not to redesign a product, but to bring stability to how it behaved under challenging conditions. In many ways, this reflects the broader point. Innovation often comes from individuals exploring questions outside the constraints of traditional product development. I didn't have access to trade shows, technical roundtable discussions, standards workshops, or external research funding, but I stayed curious. Control theory I had developed was eventually applied in a working system, an autonomous control logic built using standard components already found in the industry. Sorry. It didn't require new sensors or specialized hardware, just thermocouples, airflow control, and a microcontroller. The system was certified by both EPA and international accredited test labs, demonstrating that this approach could meet performance and compliance requirements. Importantly, it was implemented across more than one heater design without being re-engineered. This helped demonstrate that the logic wasn't dependent on any single stove architecture. While not intended to replace innovation in product design, this approach was meant to complement it by making existing systems more adaptive, not more complex. This is just a conceptual demonstration grounded in well-known engineering principles. It is meant to illustrate how electronics can help address a very difficult problem in combustion stability. I'd also like to make clear this is a systems level model, not a mechanical fix. I started from a familiar realization that combustion systems are dynamic and everything we add to them becomes part of the system. Materials, sensors, components, fuel, air channels, they're all influencing energy flow and behavior. You can't separate them. So instead of trying to control every single input or variable, I treated the stove as a dynamic energy mesh. Like we use in computational modeling, CFD, robotics. I focused on stabilizing the system's energetic centroid, much like controlling the center of mass in motion platforms. If I can stabilize a centroid, I stabilize the entire system. Electronics made it possible to see this in action. They let me observe energy flow, adapt across stove types, and apply corrections hands-off without redesigning the stove. This approach naturally lends itself to neural network architecture, adaptive, responsive, and design agnostic. Although that architecture was conceptually outlined during development, it was not formally pursued. To be clear, though, there is no single method here. What matters is stability, adaptability, and autonomy across fuels, designs, and user behaviors. As we talk about the potential for electronics and wood heaters, it's important to acknowledge the very real constraints that manufacturers face. Product development cycles are driven by practical needs, meeting emissions and safety standards, ensuring manufacturability, keeping costs in check, and delivering a product to market on time. These are complex projects with multiple moving parts, and they often leave very little space for deep research or experimentation. While innovation absolutely happens within these cycles, it tends to focus on known problems and known solutions. Things like improving air pathways, refining combustion chamber geometry, or integrating better materials. This is not the same as conducting research into adaptive algorithms or system behavior under variable conditions. And from a resource standpoint, asking a product designer to take on a long-term R&D initiative, especially something involving control theories, sensors, microcontrollers, and field validation, is just not feasible in most organizations. It requires time, funding, and often a different kind of expertise. Even when manufacturers are interested in electronics, they still face difficult questions. How do we integrate this? Will it affect compliance or safety testing? Can we build it affordably? Will the market accept it? These are not easy challenges to solve, and they're part of why progress has been slower than some might expect. Next, we focus on what's already pushing innovation forward. External research and funding programs give space for deeper experimentation, something many manufacturers can't support internally. Cross-sector collaboration, when labs, agencies, and developers work together. This helps move ideas from research into applied systems. Independent innovators also play a critical role, showing what's possible with limited resources and existing tools. Design agnostic solutions and professional development are how we scale this. These are mechanisms already proving helpful. Now let's shift to where this could go. Not what's happening, but what's possible if we finally embrace electronics and wood combustion. We can move beyond stability into smart systems that learn, adapt, and self-optimize over time. We could design around principles, not fixed products. allowing stoves to be simpler but smarter. Imagine the impact on consistency, on emissions, on user experience. But to get there, we need to support open systems, share knowledge, and be willing to treat combustion not as a solved problem, but one worth solving better. I want to emphasize that we're not starting from scratch and progress is already happening. Electronics-based control systems have already been successfully tested and certified through EPA and international accredited labs. This isn't a concept or prototype anymore, it's a proven functional reality. Many of the experts helping shape these new test methods and standards are also hands-on practitioners. These aren't just policy voices. They're the same people down in the lab, running test equipment and test methods, preparing fuel loads, collecting data. They understand the nuances of wood heat from both the ground and the meeting room. Electronics and control theory are already in action across related technologies, pellet stoves, hybrid systems, and heat pumps. These systems show that the leap to electronics of wood stoves isn't as large as it once seemed. The principles already work elsewhere. We're also seeing important federal and institutional support, like CRADA's DOE-funded initiatives and lab collaborations. These programs are investing in the technical groundwork that helps bring control systems from theory to field application. With a blend of field data, practical testing, research insights, and innovation in product development, we now have the tools to stabilize wood combustion. The path forward exists. We just need to walk it. As I wrap up, I want to touch on some of the most common questions I hear. Is variability the problem? The short answer is yes, but it's important to clarify what that actually means. There are incredible designs out there, well-engineered, efficient, and clean. But the reality is that even the best designs are still vulnerable to external variability. Things like inconsistent fuel, how the stove is operated, and the condition it's used in. The idea here isn't that design doesn't matter. It absolutely does. It's that design alone can't account for everything. That's where electronics come in. Not to replace design, but to help designs adapt in real time and remain stable in the face of real-world fluctuations. So the challenge isn't just combustion, it's the environment combustion happens in. When people hear electronics, they often picture complex, expensive systems, but that doesn't have to be the case. Today's hardware is affordable and powerful. Simple sensors and microcontrollers are inexpensive and can already do a lot. A basic setup might just prompt the user to reload or adjust a damper. That alone can reduce variability. And then for more advanced goals, we can scale up. Adaptive logic, sensor fusion, even machine learning. The point isn't that everyone must jump to neural networks, it's that electronics give us options. What matters is how we apply the technology, not how complicated it is. The barrier isn't necessarily cost, it's mindset and willingness. Training and standards absolutely matter. They're critical for safety, consistency, and performance, and we've made huge strides in both areas. But even the best user manual can't react to what's happening inside a stove in real time. Real-world combustion doesn't follow a script. Wood varies, environments shift, users behave differently, and that's where electronics come in. Electronics can do something a manual can't, observe and adapt. Whether it's a basic indicator or an advanced logic system, they can help us respond to conditions as they happen. So yes, standards and trainings aren't key foundations, but electronics fill the gap where those tools stop short. As we wrap up, I want to leave you with a few key thoughts. First, wood heating is inherently variable. Every fire, every home, and every user introduces change, but that doesn't mean it can't be stable. Smart controls grounded in sound theory can respond to that variability and help these systems perform reliably, not just in the lab, but in the real world. Second, electronics aren't just a feature, they're a bridge. They allow us to connect product design with adaptive performance. But more importantly, the thinking behind the controls, how we model systems, how we manage inputs and outputs, that's where real impact happens. And finally, this work doesn't happen in isolation. Innovation is strongest when we include voices from all corners, designers, testers, researchers, and independent inventors. We all see the problem from different angles, and solving it requires that diversity of thought. In terms of next steps, I believe we need to broaden our support for R&D across the industry. That means creating more space for technical voices in product and policy conversations, and making sure the solutions we pursue are not only compliant, but scalable, affordable, and field ready. Thank you again to the Alliance for Green Heat for creating this platform, and to my current employer for supporting me to participate. I've never had this kind of opportunity before, and I hope it's just the beginning of more conversations that are driven not only by innovation, but by inclusion, transparency, and a shared commitment to cleaner wood heating. Thank you, John.
Thank you, Ken. That was fabulous. Your voice, I really appreciate your optimism and inclusion and practicality. And you shouldn't. I think yours is an important voice in this industry, and I hope it gets out there more frequently. Our next speaker is Paul Laporte. I'll give him a sec to load up his slides. And I'll also like to say, if anyone knows of automated stoves that were not on the list that I originally showed, please send them to us. We may have omitted some, including right here in North America. I guess there is a distinction. I think there's been a lot of experimentation, which has brought partial automation, which is also valuable. And the trick is if you have automation plus user control, which can override the other. So as long as the automation can override the user's demand for more or less heat, then we would consider that a really mature, fully automated stove. Okay, enough of me, Paul. Paul is the CEO of MF Fire and product lead for Fire Maps and the company's AI and digital solutions, including wood stove automation, real-time monitoring, and emissions reduction. Paul possesses a BS in aerospace engineering from MIT and an MBA from Georgetown University. They say that burning wood isn't rocket science. It's even harder than rocket science. So I'm glad that you have some aerospace engineering to bring to it. All yours, Paul.
Thanks, John. I was going to put on the video, but I don't seem to be able to do that from my end at the moment. I don't know if there's a setting on. There we go. You guys gave me control. Thank you. Good afternoon or good morning, everyone, depending on where you're joining from. My name is Paul Laporte. I'm the lead on a lot of our automation stuff here at MF Fire. And as kind of an interesting connection point to something John was showing when we first got started, this company spun out really of the design challenges back in 2013 and 2014, when our two founders, Ryan Fisher and Taylor Myers, assembled a team from University of Maryland, went on to, in both of those, to win the low emission prize. And they realized they were onto something. And so where we are today is really partly due, John, to those efforts, or we wouldn't be sitting here. So thank you for that. Today, I'm going to go ahead and talk about why wood heat's future depends on automation. I think it's important to have a little bit of context. For the past 10 years, MF Fire has been really focusing on developing some innovative wood stove technologies, a lot of it driven by technology and various levels of automation. We'll talk a little bit about some of the things that we have done along that path where we are today and why automation is going to be critical to the future of the industry. So really, what's at stake here? Well, first of all, we're focusing on how do we continue to improve the emission profile, both of a lab-tested stove as well as in the real world. The real world is what I'm going to focus on because that's where the majority of emissions come from. We're also looking at how we can improve efficiencies and continue to make wood heating easier for a larger number of people. A lot of times we have an individual at home who might be the person who runs a stove and nobody else touches it because they don't know how or are afraid of it. And then bottom line is we have to deal with this, at least in the US, these EPA regulations, which are kind of a shifting landscape and are substantially behind the times. And that's not to say that the EPA, is doing that, with ill intent. It's, you have to create standards. And unfortunately, we need to find a way to create some standards around automation and, get at the root of the problem where most of the problems lie, and that's, as you'll hear, a little bit more user contributed emissions. So with that, wood heat's pretty simple. We think about it like, hey, we open the stove, we throw some logs in, we build, start a fire, and we enjoy the heat. However, as you heard from Ken, wood is very complex. That wood combustion cycle, it's very unpredictable, and it's very sensitive to all kinds of different things. It's sensitive to primarily the timing of different events and actions that go on with that stove, from when you shut the door, when you engage the bypass, when you reload, how fast you get the temperature up to speed, and then all those environmental things that impact and make fires, each fire a little bit more unique. So every fire is different. Every fire and every stove is different, and you can't optimize for all fires and all conditions all the time, and timing is everything. On the right-hand side, you see some examples of different kinds of variables, and the list is much longer than this. And the way that they interplay on any given day, any given moment in any given household can create a variety of things. One day you have a very clean burning fire, one day you have a very smoky fire. Some days it's hard to get it started, some days it just roars. So dealing with this complexity is one of the things that automation can help us to do. So 600%, that's a really large number. 600% of what? Well, turns out that users, as John talked about and Ken alluded to as well, users are the problem here. I mean, we're the users. It's not just any one particular person, but you take a lab test of a stove that's very prescribed. You do exactly this step at exactly this time, and you get a certified stove. You meet the requirements. However, you throw it out into the wild, and with all this variability comes chaos. You end up with, there's been several studies that have shown that you can actually, a 2 gram an hour stove can produce 12 grams an hour of pollution over the duration of the burn. And a lot of that comes from single ill-timed actions. So the reality is physical design of a stove, and no slight intended to any of my manufacturing competitors out there, our brethren in the space, but there's only so much you can do in designing a steel box. And you design a steel box as limited controls. It has limited controls primarily because the regulations say we have to have limited controls. And when you have limited controls, you can't tackle all that variability. So we're seeing diminishing returns from stove design. And so now we need to turn someplace else. Where do we get that? Well, one of the places that we can get that is by moving to a new arena. Right now, instead of taking physical innovation, let's go ahead and start to talk about automation. Automation is it presents some great opportunities, but it means a lot of different things. And I'm going to organize my thoughts into 3 categories. First one is monitoring the fire. This is where sensors can come into play. So we use a lot of sensor technology to measure things from as simple as we've been measuring for a long time in the industry, temperature. And there's third-party organizations out there who have PM monitors. So you can measure all kinds of things coming out of the chimney. But monitoring fire is the start. And you want to be able to monitor that information because with that data, you can do a lot of different things. The other part of automation is now you can use that data to control the fire. And we'll talk some of the things that we've done in this area. And there's some good innovation going on, but controlling the fire does have some limits. And they're primarily externally regulatory limits, in that you can't take great automation technology and deploy it against existing stoves. That's a big problem. So that brings us to the third category of automation, which is about empowering the user so that they can control the fire and become an expert and effectively cut out a lot of that user contributed emissions and the bad performance, because they now are doing the right thing at the right time based on real world data in real time. So as we look at monitoring the fire, this is like the low hurdle rate of what you have to be able to do to get started. Now, there's a bunch of different things that you need to be able to monitor. Temperature, is the big one. Temperature tells us almost everything we need to know if you have all the appropriate context around it. But you have to know what that temperature is doing. Is it going up? Is it going down? Is it accelerating? Is it slowing down? Then there's a whole bunch of other things. Where in the burn cycle is that temperature behavior happening? Is it during startup? Is it happening during that long tail as it's burning down? What's going on with the other controls? Is the door open or closed? Is the bypass engaged? These are all the data points that when you take them in, and if you understand them, you can make certain things happen. But as I mentioned, fire is very sensitive. A small change, if you shut the door a few minutes early or a few minutes late, it has a huge change to the amount of emissions that go on. A 5-minute difference can double the emissions over the total emissions over the course of the burn. So when you have that level of sensitivity, getting it right and getting it timed appropriately is very important. That means all of our sensors realistically need to be real-time sensors. Here's some examples of sensors that we've used over time, and I think it's good to kind of just make it feel real here. So starting in the upper left, you have some examples of door sensors. We've built door sensors over time, starting back with our first product. They had a physical door sensor, and mechanical things tend to wear out and break. So then we went to a different kind of door sensor that we were using on products using IR or infrared. Then we switched to a laser door sensor, and now we're even playing around and doing some stuff in some of our newest products with computer vision, which is an AI-driven camera system. So there's some pretty cool stuff out there. As you kind of rotate around, the stuff on the right, this was actually the controller that we had mounted on the back of our Catalyst wood stove. And as you see here, we actually had 3 thermocouples that were being used, 2 that were inside the stove and 1 that was air gap behind the stove. And that gave us room temperature so that we could use the room temperature as the guiding light. If you wanted, from a user perspective, I don't need 500 degrees or 1,000 degrees of heat in my stove. What I need is my room temperature to come up to 70 degrees. So we approached it from that point of view of like, all right, we want to measure how the heat is rising in the room, as well as what was going on in the firebox. Then down at the bottom left is an example of one of the beta test units from our FireMaps application that we did with the DOE here a few years ago. So a lot of really interesting things. You need to be able to have all these different kinds of sensors out there, because each of them will give you new data points that can factor into what it is that you need to be able to do. So if data alone doesn't help, you have to turn that data into something actionable, and that's to find a better way to control the burn. So let's go back and talk basics for a second. Fire triangle. There's only 3 things that come into play here: oxygen, the fuel source, and applied heat to get a combustion process started. Now, you can control wood once every load. You put it in, and that's it. You apply heat through tinder and some other things, that's it. However, airflow, the oxygen, is what you can control, and you can control that conceptually second by second. And there's a lot of ways to do that. You can do it up in the chimney and pull air up through. You can do it at the air inlet and force air in. You can do it within the firebox and have extra air coming in through the manifolds or through an open door. So understanding that airflow is the main thing that we have to work with here, And if you can understand behind the scenes what's happening with airflow, you can do a lot of great things. Now, what we basically did was we went out there and took one of our founders, Taylor Myers, who's got a PhD in combustion science, and we said, we need to put this expert in a box and put it in your living room so that it can help you, because you're not going to sit there and control airflow every second over the course of an 8-hour cycle. Just not going to happen. But that's what you need to be able to do as conditions change. As your draft conditions change, as the wind changes outside, all of that can come back to the temperature within the fire. So we basically took Taylor and we stuffed him in a box, and we used his expertise in the form of some algorithms and computer programming to do what we needed to do. So this is an example of a fire that we have visualized through some cloud tools on some of our products. And it just gives you an idea of, like, you can monitor the cycle and what's going on. And when you can do that, you can start to take action. This was the very first product that we created back in 2016. It was called Catalyst. It's no longer on the market. It could be, but I do think that we ran into some challenges, not with the product, but with market adoption. And so we decided that we weren't going to move forward with that, as we had to do a couple $100,000 renewal cycle with the EPA. Now, airflow control is critical, but because of EPA regulations, it really is a one-off thing. You build it purpose-built into a stove, and that means that you're limited with what you can do. And that means you can't make a very big impact one stove at a time selling just new models. You really need to go back and be able to tackle that 13 million install base in the US and 100 million overseas. And so we really do need some standards to come out in industry for this that are regulatory controlled. And we can take that 600, cut it back down to about 80% of the standards get cut out. What we really want to do is empower the user. I know I'm going to run out of time here. About a minute in, but our focus lately has been around empowering the user, because there's no regulations there. If I can monitor all the data, I can then provide guidance instead of having the stove automatically control it, that tells the user to do certain things at certain times. And we're doing that through FireMaps, which is our automation platform. And we've seen this result in an extended trial and up to 58% reduction in user contributed emissions, which is multiple grams an hour. It's pretty large. And we think this is where we're going to take our efforts in the future. These are some examples of the app that the user would see and interact with. But a lot of intelligence is now moved, taking the data from the stove up to the cloud, do some serious processing, and then send back down real-time alerts, guidance, and information. So in summary, there's a lot of stuff going on. Wood fire is incredibly complex, but the user is what helps to create the emissions that come out of that. And since stove designs, the physical designs, have kind of reached near their limit, we really need to focus on what we can do to control performance moment by moment. Automation is going to unlock the next wave of that. And we believe that the real-time monitoring, when applied with dynamic airflow and then the real-time guidance, is what gives us the best bet for really reducing emissions and boosting performance over the long haul. So thank you.
No, thanks very much, Paul. That was great. And let's just say, MF Fire is really a case of a company that's made use of some of the grants from the DOE. And it shows how, very small support, government agencies can really help industry in the transition period, rather than just pouring, millions and millions into tweaking our test method, which has been what's happening lately. And I just don't think we're going to get the kind of results in the field that all that time and effort is promising. So next up, Hugh Wells. Hugh, you can bring your slides up if you can. Hugh, like many in this industry, is part of a family company. His company, A.J. Wells and Sons, was founded in 1972 by Hughes's grandfather, uncle, and father. Hugh started in 2002, working in the factory, which is on the Isle of Wight, a small island on the south coast of the UK. And now he works alongside his uncle, 3 brothers, 4 cousins, and a son. He's also vice chair of the Stove Industry Association and the maker of Charnwood E700, I believe, which is a fully automated stove. So, Hugh, it's all yours.
Great. Have you got my full screen there? I'm just trying to look what I'm showing you, but that is the full screen, isn't it?
No, go ahead and click the slideshow little button up there, and it will give us
Is that better?
It's in presenter mode now.
It's in presenter mode. Okay, let me switch that. Sorry. You did that. Tell you what, let me just stop that share and I'll just go back to that. Sorry about this. Let me do this is better. You've got it, should have it there. Is that correct? Have you got it now?
Yes.
Good. Excellent. Well, thanks so much for having us here. We're from the UK, so it is, I don't know, 5:30, 6 o'clock even in the UK in the evening. And I just wanted to tell you, as John said, we have got a stove on the market currently in North America. And I want to just tell you a little bit about the story about where we've come from and how we've got to the place that we are. So we, and this is not, everybody probably watching this knows this, but to get good wood burning, you need a good heater, a good stove. I think this is, I did this slide for Australia and they call them heaters, but it's stove in the UK and stove in the US, I think. So we'll call it a stove. A good stove, good wood, good fuel, and a good user. And I think if we're honest, the problem often comes with the user. Even us that think we're great at using stoves we forget about them, we sit down, we forget what we've done, and we end up not being very good users. And then that doesn't account for the people that really don't know what they're doing, and you know, they load the stove, crack the door, forget about it, shut the door, close it down too much, it all goes black, all goes horrible. And however much we say, we know it's the user that is always the weak link. And so about 10 years ago, and this is the story of the Sky 700, we started looking at automatic stoves. How do we take user error out of a stove and actually get good laboratory burn conditions all the time? And so we started looking at electronics. In fact, we'd actually done a little bit on electronics with a previous stove we had. It was a very basic stove, but basically when you shut the door, it would open the air for a little bit and then close it down. And so we knew a little bit about it, but this was nothing, it was very, very basic really. And the idea was that can we do it to an automated stove, an intelligent stove that people would choose to use. Now, in the UK, we have a thing called DEFRA exemption. When DEFRA exemption came in, it was one of these weird things that government needed it, they wanted it, but basically it meant you couldn't shut your stove down. And so the problem is that if you can't shut your stove down, it was always overburning a little bit. And so people would buy these stoves because they had to. It was legislation, certainly in smoke control areas, but they never really liked it. And if they could, they would just take the DEFRA stop off and they would have it as it was not intended to be, because it was a bit of a hindrance. And so we thought, if we're going to design an automatic stove, we need a stove that people choose to use. We don't want a stove that people think, well, I've got to use it because legislation is dictating it. We want a stove that people say, I want that stove because it is the best. So that was our remit, if you like. And to be honest, it started off a bit like a hobby project. Al, my cousin, who's very good on electronics, very good on lots of things, aerospace engineer, in fact. So we've got lots of aerospace engineers in this industry. He started doing when his kids were swimming, and he was messing around with electronics and programming and stuff like that. And that's how it really started. And at the beginning of 2019, a company we work with in Canada, Impact Distribution, in Quebec, I had a call. I spoke to Steve, the owner there, and he said, look, there's new regulation coming into North America, and it was the EPA 2020. And he said, I think, and the reason we worked with him was previously, many years back, he said, I think there's a really good opportunity. So we thought, well, okay, if there's an opportunity there, well, we're up for that. And so I went out to the actually west coast of the US, and we went up the west coast of the US, starting in San Francisco, driving up through Reading, and we'll say a bit more about Reading because that's where we've got a bit of a distribution going on at the moment. And we went all the way up through Oregon and Washington, and ended up on Vancouver Island. And we saw various people on the way, and we thought, what would, is there an opportunity for Charnwood, a small little British manufacturer? We did quite a lot in Europe, but is there an opportunity in North America? And we thought yes. The problem we had, though, is that our stoves and European stoves generally are shaped in a particular way that don't really lend themselves very well to the EPA testing. And we knew this from before, when we tried before, and we'd been reasonably successful, but we got a product that worked and through EPA testing, but it wasn't a product that really took off. And so we so we thought, well, how do we do this? And we thought, well, hang on a minute, we've got this intelligent electronic control. Why don't we introduce that onto one of our stoves, and that can be the basis of our EPA 2020 stove? The problem is that this was our perhaps slightly naive planning, but it was what it was. This was in summer 2019. The next HB Expo was in New Orleans in March 2020. So we thought, could we have a stove ready in time that passed the EPA, because we wouldn't be allowed to burn it if it wasn't available. Sorry, it wasn't EPA. So could we have a stove ready for that time? So we thought, well, we've got this electronic control. We had an existing stove, which we thought was a possible shape for the North American market. Let's try and put them together. Let's try and get it through EPA testing, and let's bring it to the show. And we did. Amazingly, we did it just in the nick of time. I think it was about a week before. So the EPA guys were coming around looking to make sure that we had all the right things, and it was. And that was it. That was our stand. I don't know who was in New Orleans at that time, but that was our stand. I think we were highly commended in a Vesta award. We didn't win overall. If I remember rightly, I think it was the Napoleon Smart Stove that won. So we came in second place, which we weren't bitter about at all. No, we accepted, because actually what was really good is that there were 2 intelligent stoves on the market, or being brought to market at that show. And that was good, because actually this was a new concept. And actually, we don't want to be the only ones doing it. We want to have competition in the marketplace. And that's why what you do at Alliance of Green Heat is such a good thing, because actually it gets the best brains together and hopefully makes us innovate better. Now, anybody that knows about March 2020 was the start of COVID. And so Donald Trump, the president at the time, the president now, but he decided to kick, well, many Europeans weren't allowed to come into the US. We, being British, thought we were doing well, until the next day announced that no British were allowed either. And so we had to quickly leave the show. I think it closed half a day earlier, get back to the UK, and we were on the last flight out. So we got back in the nick of time. But we had launched an intelligent stove. So finally, it gave us a bit of an opportunity to really start looking about further development. We had it was EPA tested, it was safety tested, but there were still some tweaks to get it ready for production. And actually, we took that time during COVID to do that. So finally, we launched it into North America in summer 2023 with a container load going to Quebec. It was quite a small scale, but Impact Distribution, we worked with them and some of their dealers, and we got the E700, the Charnwood Sky E700 into North America as a fully functioning intelligent stove. We then brought it to Europe, and we launched it into Verona. And I think some of you may have been there. I think we spoke to some of you out in Verona also. So when we were looking at the development process, it was very much that our design technology needed to go into, we wanted to put it into the stove, and it must perform well in the home, as well in the home as it did in the laboratory. Paul rightly said that, you know, we want to get, in real life, stoves often don't burn cleanly or efficiently compared with the test environment. And for us, this was a no-no. We had to get real test performance in a domestic stove. So that was the first thing. Secondly, we wanted to make it possible to the people, it would be suitable for everybody. It's very easy to get a techie electronic stove, which everyone's a bit frightened of, and that was not what we wanted to do. And secondly, it had to burn well. It had to look really well. It had had good burn and burn nice and cleanly. And that was our thinking behind it. We also said that it's got to work straight out the box. Some people are techie people, they love all the gadgets and stuff. Some people don't. So we want a stove that you can just literally plug in, switch on, and it works. It can work with an app that we do have, but it also needs to work with a button as well. Not everybody wants to run a stove with an app. Electronics, there's a bit of a resistance to having electronics on stove. And so that we were saying this is what we need to do. We need to incorporate intelligent technology, but in a stove that really works for everybody and not just the techies. And actually, that is what we managed to achieve. It was a stove that actually quite surprised us, because I think if we were honest, we thought it would be fairly niche. But actually, it was a stove that people got and said, this just works. You know, that it actually is easy to use. It's easy for a person that doesn't know how to use a stove. So actually, some of the dealers in the UK that have sold the most of these, actually are the older dealers that are selling to older customers that are not actually that au fait with stoves, and they just want something that works. So they say, this is a stove, I don't want to continually mess around with it. I literally just put the fuel in, I light the fuel, I close the door, I leave it, and it just goes. And when it wants to be reloaded, it tells me. Equally, it might be time poor people, professionals that come in and out, and actually they haven't got time to be fiddling around with a stove all the time. And actually, people like me who thinks they know about a stove, and I try and I would back myself to run a stove, but actually, you know what? I forget about it. And actually having a stove there that I can just literally leave it, I can run it and light it and go away. It does just work. So the other day I was going to an exhibition. My wife said to me, "Could you light the stove before you go out?" Because she was giving me a lift to the well, we live on an island, so it was to the boats, and so I was going to get an airplane to Italy, and I totally forgot to do it. But with the E700 we had installed, I could actually light a match, put the fuel in, shut the door, and leave it. And 3 hours later, she came back and it was going, and she just loaded another log on. So that is the beauty of that technology. So in North America, it came in 2023. Europe, it came in 2024, and we launched it in Australia earlier this year. Coming to test figures, so you can see what happened here. The first test we did in the US, we actually got 2.5 grams an hour of burning, which we were very pleased, because that allowed us to go to the show. However, as you may know, the EPA had to do a load of retesting for various reasons. So we retested it, and we actually ended up with 1.66 grams per hour, which was pleasing. The Australian test results, we ended up with, again, different tests, 0.3 grams per hour. And in Europe, we actually end up that the efficiency is measured slightly differently. We've got 89% efficiency, but actually it comes out about 0.25 grams an hour, or actually we measure it slightly differently, but that's the equivalent. So we got some pretty good test results. And one of the questions John was asking is, what what do we face when going to test labs? Because automatic stoves, intelligent stoves, will require a different set of a different sort of way of testing. And we did find this. So things like overfiring. How do you overfire an automatic stove? You know, when it reaches a certain temperature, it starts to close down. And so that was so that was one of the things. Now, we agreed with them that if we put it onto the maximum temperature and unplugged it so it couldn't move, that would be suitable for an overfire. But I think those are some of the things. And actually, we need to be fair on automatic stoves to make sure that we sort of test them similar to what we do in a manual stove. You know, if you there's a whole big debate on that, and that's probably something we can go into later, really. But it is we do need to consider how we test these stoves well. So just very quickly, because we're coming to the end of this, how it works. We use 3 controls. We use temperature controls, we use room set control, and we use an flame intensity sensor. And the reason we do that really is because actually we always find in our test lab that we can look at the fire and say if it's a good burn or not a good burn. And that's what we try and replicate. So we look at the flame, we say, okay, what does the flame look like? Is it dark? Is it light? Is it smoky flame, whatever? And we look at the flame using light sensors, and that's how we measure it. We control that with temperature sensors as well, and obviously door opening. And those 3 things together, we put into a microprocessor. It comes out with all the algorithms and all the different things. And it's taken us ages to do it, but it works kind of really well. Let me just play this very quick video if I can, and you can just see it working in action. Work.
The Sky E700. This stove uses Charnwood iBlue combustion intelligence. A microcontroller continuously monitors the state of the fire and optimizes efficiency while radically reducing emissions with real-time adjustments. Air is introduced just one. Exactly the right to ensure care. Introducing more or less air when and where needed, burning the wood in the cleanest.
So I don't know if that audio worked, but we can send the video out later, and you can see that. But just finally, it comes with an app. It tells you when it needs to be reloaded, all those things you'd expect. You can control it. You can control the intensity on it. You can even put it on manual mode, so you can make the fire close down and open up. But it's not good on manual. It looks great on manual mode, but it's not the cleanest burn. And that's what we're always trying to do: get the cleanest burn. So it comes with that, but equally you can just run it on a button on the front of the stove. And just some of the things, what we've actually found in real life, it uses less fuel. It uses about half the amount of fuel. Now, it is, you know, in Europe, we've got 89% efficiency, and so it is efficient, but that's not the reason. The reason is because you don't forget about it. So in real life, it's always optimally burning. And, you know, that if you can burn half the amount of fuel, that's what people say. Some people say it's 40% of the amount of fuel they burn. Some people say it's a bit, maybe 60% they burn, but it burns a lot less fuel. And if you can burn a lot less fuel, a lot less emissions. So that is one massive bonus. But of course, you know, it saves money as well. So that's really good. It burns very cleanly. So the glass always looks good, always clean. And it's really low emissions. So, you know, for governments love it, because actually genuinely it is test house performance in real world. So I think probably my time is up, but that is us. That is what we've been doing. Thank you ever so much, and I'll hand back to John, I think.
Okay, thanks so much, Hugh. That was great. You know, I'm glad you fessed up that you had a hard time controlling your stove. I thought I knew something about burning wood stove, but I too found I'd look out my window periodically and I'd see all the smoke coming out of the chimney. And I got frustrated because, I live in a pretty densely inhabited neighborhood. So that's when I switched to a pellet stove, realizing that I simply didn't have the time and wherewithal to pay enough attention to a wood stove in a densely inhabited area. Hey, one other thing I want to mention before we get to the questions, I don't think any of you guys mentioned, but one of the great things about automation is it helps regulate stoves in different settings. If you're at high altitude or low altitude, if you have a long stovepipe or a short stovepipe, it's actually the installation of the stove has a lot more to do with how the stove burns than people realize. And that's another thing that controlling the oxygen can really help. Hey, Darren, you want to run that last poll before we jump into questions? And okay, so what do you see as the biggest barrier to integrating electronics into wood stoves? The cost of technology, consumer resistance, complexity of maintenance, lack of regulatory support, or I'm not sure. And we'll just leave that up for a couple seconds. Looks like, it's a close race between cost of technology and lack of regulatory support. I don't know if you guys can everyone see the results?
I'll share it in 1 minute. I'll wait till the numbers stop moving
Okay.
around a little bit, and then I'll share it so you can see.
Okay.
I think it's good to go, actually.
And we have some good questions. The very first question someone put in at the very beginning of the webinar, I think is one of the best that we'll start with.
So it looks like cost of technology. About 41% of y'all think that might be the biggest barrier integrating electronics. But not far behind is lack of regulatory support.
Hey, John,
Right. Yeah.
I would throw out there a counterpoint to that. As you know, we were selling from 2016 on, and though the state of the the industry is changing and acceptances are changing as new people flow in, consumer resistance was very much an issue, and I'm betting that it's still a big issue because there's just a strong feeling that wood heat is simple. I like it because it's not technology driven. It's not connected. It's not powered. I think we're getting there, but the cost of the technology from our own personal experiences over the entire life cycle of that stove certificate wasn't the technology cost. It was the percentage of people that are willing to embrace it. And hopefully, as enough manufacturers have a viable option that they bring to market, consumers will start to embrace it because they'll see it more.
Yeah.
I was just
Yeah,
going to
I
say
hear-
something, Joe. Sorry. I was just going to
Go
say
ahead.
something is about the cost of technology. There is stoves out there, like I created stoves that actually commercialized in North America that went through the EPA accreditation and so forth, and they have electronics on them. So that's just saying that went through a product development cycle, and they were very low cost, and they actually exist. So they're commercially available. So through a manufacturer.
I've heard some manufacturers say the goal is to hide the technology and hope that the consumer doesn't realize what's in the stove. I mean, we don't really know or care how much technology is in all the products that we use during our daily life. We just want to know that they're reliable, and that they don't break. And they all seem to be getting more and more sophisticated. But so that leads us to the first question. Here's a guy who says he's all for tech, but he says tech's technology glitches, it bugs, it fails. So I guess the question is twofold. One, are there going to be more callbacks, more people that are, calling the manufacturer with issues if they're tech glitches? But also, what happens in a power outage? Do these stoves work without electricity? Or even if they're not a battery backup, what happens with no power whatsoever?
Do you want me to answer that one? Our real life experience. Obviously, we've got probably about 500 or 600 out there, probably more than that actually now. But yeah, I mean, look, the technology isn't that complicated, really. It's clever, but we've tried to make it very, very robust. So we don't use stuff like lambda sensors. That's why we use flame intensity sensors. And we use temperature sensors. So if there is an issue, you could easily replace stuff out. So we haven't had a massive, see, when you first put stuff into the market, there's always some teething things, but it's comparable with normal stoves we put out there. In terms of power going off, that's a really interesting one. So if power does go off, obviously in what we've done, it will stop in the position that the air control was last left at. Now, what that then does is you've got two options. One, we supply a little battery pack, a little 9-volt battery pack. You just literally break it's got a little jack that you just break, put the battery pack in, and it will run itself for a few hours. You can get a bigger battery that'll run itself for a few days or weeks, even if you get a massive battery. If you know that. And then that will then return to normal operation. However, we also have a little mode on the stove that puts it into what we call power cut mode. And effectively, you can just press a button on the app. It sets the air into a position which you can still run the stove, but it won't be automatic. So if you were lighting it, you might have to crack the door, for example, just like a manual stove. And if you were, once it's going, it burns at a steady rate, but it doesn't shut itself down. But it allows you to still use the stove. So if you know your power is going to be out for a few weeks, you can easily do that. So that's what we found. It seems to work very well. But yeah, there will be different problems, but not insurmountable.
And to echo what you said, we found the same thing with Catalyst. In a power out situation, you have to have effectively a single burn rate mode that is acceptable for what that burn rate needs to be able to achieve a good fire. But it may not be optimal for a lot of different things, but you're not going to freeze to death. And I think that's what people are most concerned about. Like, make sure I can still get a fire no matter what.
And there's also, just to echo what Paul and Hugh said exactly, and in my case, it wasn't controlled burn rate across the board. So you had full manual control, and you got an autonomous controller in the background. So you can have situations where you set it at, like, if you've got a single burn rate setting, but you can also have it where it defaults to something that works across that whole range. So in reality, and it was kind of my goal, is you still have an operating range. You're not fixed to one thing, because that's one thing customers will really say, well, it's cold out and I want to get my stove going and the power's out, right? So, all these things come into play. And like Hugh and Paul said, you set it and, you put that consciously thinking of that situation that happens, whether it's battery or completely power out, and the operator can still operate the stove.
Okay. Here's a follow on. How many watts of are these automated systems consuming?
Ours is about 4.
It's pretty modest.
I was just right. I just managed to get rid of one of the questions that came up about price that somebody asked. I clicked the wrong button, but just to give an idea, it's about 4 watts. The price slightly dependent on tariffs at the moment, but it should be around about $5,500 US. And there was the firebox volume was ours is quite small, isn't it? It's about 0.58. Yeah.
It's 0.58 cubic feet.
Yeah.
Or meter. You're probably doing in meter, 0.58.
Well, this is feet. We don't even do 5 watts. Oh, no, we do 5 watts not here, but it's a bit different. But yeah, no, that is 5.8 cubic feet. I think that's right, isn't it? Yeah, that's right.
Okay.
John, yeah, one of the things that I think's kind of important to note here, we're all talking about the technology to do some level of automation. And I think that's good on a forward-looking basis. However, because at least in the US, every stove has to be certified and then locked down. And so you have to be very, very purposeful about building this into a specific model, testing that model, and you can't make any changes to it. So I can't create something that Hugh could use or vice versa. I can't go out to something that's deployed in the field and get 100-fold improvement by deploying on other systems. And I think therein lies the big opportunity if we could find a way for states and the EPA to actually work together and maybe say, okay, let's look holistically at solving this problem about emissions and allow some changes to airflow on stuff that used to be previously certified. If you can't do that, you're just making small incremental improvements, or you're selling a small number of units, a couple of hundred, couple of thousand. We're talking 100 million worldwide. That's the big nut.
Yeah. Here's a good question from Jack Kleiss. How do you solve the problem of people loading wet wood? Can these systems deal with unseasoned wood?
Yeah, I mean, for ours, again, what happens is that, so it depends on how you're looking at what's going on in the fire. So, as you say, you've got different flue draft, you've got different dampness of wood, you've got all those things going on. So if you load wet wood in one of our things, what actually happened is that it puts tons of primary air into it, because what it says is I need to get my temperature up to this level, I need to get my flame up to this level, and I'm gonna blast it with primary air to try and get it there. So it means your efficiency will suffer, but it does mean that it will give the cleanest possible burn. Now, it's not going to be as good as dry wood, of course, but that's what you find. I mean, you do get some weird things. We had some kiln dried wood the other day that was very dry on the outside but wet in the middle. And that was weird because that would burn on the outside very quickly and then sort of like slightly die, and that slightly confused the fire. But, the good thing about this is that actually by looking at the variables, looking at the variables that are happening with the flame, you can actually change your, we've got 3 air inlets, your primary, your secondary, your tertiary air. You can change those to try and always optimize the burn. Now, bad wood's never going to be a great burn, but it will be a much better burn with an intelligent stove than not.
Okay, thanks. Now, are there any, I think all the speakers, everyone can see the questions. Any questions in there that anyone wants to answer? Otherwise, I'll ask another. How about putting electric fan extractor to control the draft and make sure that you have proper draft like some pellet stoves have?
I think, they're all, sorry. Yeah, they're all kind of valid. It's just, as long as you have feedback. I mean, we all know in a system, you can do anything you want to a system, but it affects the system. So that will help definitely. That would help in a lot of situations, but it's going to change how the fire burns, how the stove reacts. So you're either doing a design-centric approach, or you're looking at it with a feedback system, using your electronics and adjusting, whether it be air or whatever you particularly want to adjust. But it works on pellet stoves. I mean, it kind of answers a question in a way, right? So, it's just my opinion.
So John, I think the question actually leads to a different one, which is, can automation and all these wonderful electronics and sensors and stuff be used to solve very specific problems that are not being solved today? And the answer is yes. So you can put on a combustion fan and sense that you've got a drafting issue and turbocharge the thing to get it started, so you get over initial draft. You can use it to deal with altitude related issues. You can use it to get through that startup cycle as fast as possible. So if you are dealing with wet wood and you blast it, as Hugh says, with primary air, you try to jumpstart that as quickly as possible. I think that where we'll evolve to after we get done about talking about performance of like, emission and stuff like that, which is critical, is this can be used to make wood burning much better in all conditions and deal with all the variables. So you can build in with software the ability to solve those specific things. So if I'm using a stove and I'm like, gosh, my draft stinks today, I can scroll down to the draft section and say, solve my draft thing, whatever you want to call it, from a marketing term. Boom, the stove does it. That's where we have the potential to go that you can never, ever get with physical design.
Okay. Okay, here's one that just, oh, go ahead.
I totally agree. That's really good that we can do. I just noticed the question here, John, about the flame intensity sensor, and I mean that's what's probably taken us 10 years. And that's where our patents lie, actually. But yeah, no, what we do is we actually use light sensors, so it's fairly robust and readily available technology. And what's quite clever is that we use we use a glass rod system in the side of the stove, which transmits that flame intensity information down to the sensor, and that's where it is quite clever. So that is probably the clever bit that we've really tried to. That's what's taken us a lot of time.
Okay.
But it seems to work.
Okay, just time for a couple more. Here's one that just came in. It's a really good question. What's the projected lifespan, primary components of automated stoves? I think they're asking what's, the lifespan of these sensors and everything that's not in your old-fashioned stove.
We haven't had many failures. I mean, we've actually I can tell you what we've guaranteed it, so that's how confident we are. We guaranteed it for 3 years. I mean, realistically, I think it should go on longer. I mean, with our system, I mean, it's the glass rod, the light sensor, we say should be replaced, when you replace the brick. But yeah, we've guaranteed it for 3 years. We've done quite a lot of intensive testing, cycling testing, and it should last, I would say, 5 years, potentially, probably more, possibly. It's a bit too early to say. We haven't had many failures.
And are these sensors something that the user can replace, or do you need a professional?
Well,
depends.
They are plug and play. You just literally plug the thing in and you do it. Whether it'd be better to get your stove shop to come in and do it as part of a service. Probably it's like replacing a brick, pretty much. Anybody that does anything pellet stoves, compared with pellet stoves, it's simple. So it's not rocket science.
Yeah. Okay. So Jess Sig Anderson from Denmark, I believe he runs, his lab is still EPA certified. Asks if anyone thinks that the U.S. Testing protocol will be able to change to accommodate more frequent loading patterns rather than having more static fire. And if you all have seen that question, anyone hazard an answer on that?
Guessing what the EPA will do?
I think probably none of us know quite what the EPA is going to do, period, in the next 4 years. But I doubt they'll be able to move quicker and more adeptly than they have been. Any other technology on the horizon you guys are looking at?
I mean, from a European perspective, one of the things they put in the latest standard, and this is no real secret, but they've said, the 3 things that we should be looking at is automated stoves, which is what we're talking about, catalysts and ESPs, electrostatic precipitators. And so those are the sort of the things that, and of course, you know, in truth, those three things could actually be linked into intelligent control systems. You know, we haven't, you know, none of our stuff uses catalysts. We've always stayed away from that. But, you know, you can actually imagine a scenario where you can actually get your intelligent control system to you know, open up different things, sense different things at different points. And certainly with ESPs would be very interesting that you could actually get it to pulse the ESP during any particular smoky parts of the burn. So that's quite interesting about how those could be integrated together. And I think that possibly might be the next thing people will be looking at.
Okay, I think we're going to close it down now. That's right. We want to respect people's time. It's almost 1:30. So I want to thank all of you. Again, it was really interesting and a great discussion. This will all be recorded and everyone will get the slides and recording, and definitely count on us to do something like this again. Maybe later this year about pellet stoves, which also could have much more combustion control, real-time combustion control like wood stoves. Or I will revisit this one next year. Okay, thanks again.
Thank you.
Thank you very much.